Right. So in today's program, we'll be looking at modeling a scene consisting of a teapot and a table, and we'll be defining a light source, and we'll be applying material properties for the scene, and we'll be looking at the result of the light and material properties, whatever we use. So the output of the program should look something like this. We are supposed to have three walls, backside two walls, and then a bottom wall, bottom the floor, right? And then we should have a tabletop, and we are supposed to have four legs, because the fourth leg here is actually hidden. And then we should have a tabletop, and on that we should have a teapot. So we also have a light source in the scene. So light source is somewhere from this direction. You can see the reflection which on the teapot here, which is shiny, right? The reflection here, this reflection is result of the light. So to start with, this is the basic main function that you have. Since this is a 3D program, you have depth buffer and you have enabled depth buffer. You should also clear the depth buffer in GL clear whenever you use it. And then you are defining a window and then creating it, dimension of the window and then creating it. And then you are calling the display function and the main loop, right? This is the basic main that you have. Now we are also supposed to have a light source in our scene. So for that reason, we should enable lighting. So these functions are the one which will help us to define the lighting. We had seen these functions. So you are enabling lighting, you are keeping one light source, you are selecting the shade model as the smooth, and then you are applying normalizing the scene. It helps you to calculate the normals on the surfaces while calculating the lighting effect. So these are the functions that you have to use in the main to enable lighting. Okay, these four. And then you have the display function. In the display function, you are not taking a separate init function. We are not taking any init function. What we are doing is we are, setting up our view using in the display itself, right? So I am clearing the color buffer as well as the depth buffer. I have not selected GL clear color, so the default background color that this clear will clear the frame buffer to will be black color. The background what we will see would be black because of that. And I am selecting a orthographic three-dimensional view volume of size -1 to 1, -1 to 1, and front is 1 and back is 10. Right. So I have taken something, a view volume like this, and then we are going to place a camera in the scene. So where are we placing the camera in the scene? Now imagine I have my scene like this. Take the center as the origin, right? You have three parameters. This is the camera position, right? And this is the lookout position. This ma'am had explained you in the last lab about GLU lookout, and these three parameters gives us the up vector. So you are placing camera at 2, 1, 2. That is along x-axis 2 units, y-axis 1 unit, and z-axis 2 units. So somewhere towards this corner, somewhere along this line, you have kept this camera, and you are looking at the origin. The look at is 0, 0, 0. So this camera is looking at the origin, and the up position is 0, 1, 0. So basically the up of the camera is the head of the camera is towards Y, the orientation of the camera. So basically, if you take this as the camera, right? So something like this. Where is the up pointing to? So this is the side that it visualizes. This is the lens. This is where it sees. But what is the orientation? Are you seeing it? The head of the camera, is it like this? So it's like you're taking photo on your mobile. You can take the object by keeping your mobile vertically or horizontally, or vertically reverse or horizontally reverse, right? So it's that orientation, that is what you gave in the last 3 parameters. So 9 parameters GLU lookup takes. The first one is the camera position. The first 3 parameters are camera positions. The next 3 parameters are XYZ position of the lookup place. Where is your camera focusing at, right? Where is it looking at? That position, and then the up vector. So you have kept the camera on the scene. Now, before even you do all this, you should have defined the lighting parameters and the material properties. So lighting parameters and material properties are defined using which functions? Functions for lighting and material properties. What functions do I use? Am I audible? Hello? Am I audible, guys? Am I audible? GL underscore lighting. Okay. GL underscore lighting is this. No, you are actually, this is enabling it. But which function do you use to, provide the position of the light, the color of the light, right? And GL light. Okay. How about material properties? How do you define materials? GL light FV, correct?
Or is over and reset.
Okay. Yes, Dhanush, that is right. GL light FV and GL material FV. So we would take different properties for RGB combinations, for ambient, diffuse, and specular light, and we would define some amount of shininess using these vectors. Vectors basically using these arrays, right? You can play around with these values and you will get different colored illumination depending on the reflectiveness of the surface. Basically, these are the reflectivity that you were setting up for. These are the values of, Ka for red, Ka for green, Ka for blue, and Kd and Ks, These are the specular, diffuse, and ambient property constants that you select, right? So you are specifying them here, and the shininess is basically to the power of ns what you take, right, in the specular property. So that you would specify. And using GL material 3F in the front buffer, you're selecting GL ambient as the parameter and giving this matrix, this vector as the name of this vector as the parameter. So basically, this is these values. OpenGL will consider it as ambient property of the material. Similarly, diffuse properties contains is there in the mat underscore def, and specular and shininess is respectively present in mat underscore spec and mat underscore shininess. You can play around with these values while you're trying and try to get different type of illuminations in the scene. You can change these values, play around, and try it anyway, right? And then we are looking at the intensity. This is the incident light what we take, right? The IL in the equations. Every equation we take the incident light. So we are taking red, green, and blue component of the incident lights over here. And then we are placing our light position, in the 3D world. We are placing our light at 2, 6, 3. So 2 along x-axis, 6 along y-axis, right? And z is 3 somewhere towards this area, right? But little over and above. That's why y is 6, right? It's quite at the higher level. You have selected the lighting position. You can change the illumination light intensity. You can change the combination. This is producing you the equal intensity. You can change the intensity to get the different kind of incident light, right? And you are using GLF light FV for light source GL light 0, which you enabled in main function. The position and diffuse vectors you are passing over here, and followed by our definition of viewing. We have taken the view volume and we have placed the camera. So this is the initial setup of the program. So you have defined material property, you have defined lighting, the position, the intensity, and then you have set up your scene. You have placed the camera in the scene, right? So right now you should be able to see your object, like this, because the wall what you see is from the direction. What you are seeing is basically, if you take the view volume, right, from this side is where you place the camera, right? So this angle, from this angle, whatever the camera sees is what you see. That's why you are seeing it from the corner. Actually, the x-axis would be here. You see, the x-axis of this coordinate system is basically somewhere like this. Sorry, this is z-axis, this is x-axis, and this is y-axis, right? You have it like this. And your camera is, there is a view volume. Defined in here, right? So your camera perspective is what you're seeing from this side. I hope you guys got the idea of the positioning of the camera and the lighting and material properties usage in this program. Any doubts so far? Do you guys get the idea of from which angle we are looking at is actually the angle where is basically from the visualization? What we are getting is basically from the perspective of the camera, the position of the camera where we have kept, from there is what we are seeing, right? So basically, I'll show you a simple example here. So this is the teapot that you have. This is the program that we have. I have placed the camera at 212. That's why I'm looking at 0, 0, 0. I'm looking at this, right? Now let me change the camera position. You would probably, okay, I would keep it at Z is equal to 0. So X is equal to 2 and Y is equal to 1, right? So you should be seeing the object now. Now camera is from this direction, actually. From this direction you should see. So Z is equal to 0, X is equal to 2 and Y is equal to 1. You will have camera over here, right? So from this direction you are looking at 0, 0, 0. So you should not see all three faces, you should see only two sides of it. Yeah, see, repositioning the camera will give me this. I'm looking at 0, 0, 0, which is at the center of the screen for me, right? And I am at position 1, right, above. The camera is positioned at y-axis 1, so little bit of top perspective you're getting, and x-axis is 2. From 2 is what you're getting. If I make this also at 0, you won't get the top angle at that direction. Look at it. You're not getting the top angle. The table and everything got blended back with the wall, so you would not get it. I hope you understood about the perspective of the camera, from which angle we are looking at, and how we are trying to visualize the coordinate system here. Is that clear so far? Any doubts? Please answer. Am I audible, people? Yes, lighting is fixed, meaning to say we have a light source, right? So it's basically we have a light source in the scene. That light source gives us the light. Somewhere here we have a light, and it gives an incident, light on this. The viewer is towards the camera, that is towards you, basically, right? The viewer is basically towards you. The vector towards the viewer is basically towards you, and then the normal of the surface goes like this. This surface will be illuminated based on the illumination model what we have learned, right? So yes, the lighting is actually fixed, and it is of course dependent on the viewing position, that is the camera position. We discussed about the camera position relativity, right? The angle between the normal and the, see, this is a normal. If the viewer is at 90 degree, he should not see the object properly. But if he is exactly from this side, the cos theta, right? The angle between the viewer and the normal, if, let's say this is theta, as and when the theta increases towards 90 degree, the intensity goes down. But as and when it becomes 0 degree, the intensity goes high. So that's the effect of viewer that we would have in the scene. Is that clear, Ashwin? Yeah. Okay, so I'll move forward. So that is about lighting and positioning the camera. Basically, that's about viewing and illuminating the scene. Let's try and model our, objects in the scene now. So To model a wall, what we are going to use is the glut.h function. Glut.h header gives us the glut library, gives us a function called glut solid cube, right? This glut solid cube is basically a function which creates a solid cube of whatever color you take. Now you are seeing different shades of the color. That is because of the the lighting effect. So this side is not much illuminated, but some ambient light is present in the scene. You get to see it in the darker shade. This light is more exposed to the light from which is coming from this side. That's why it's more brighter, right? So this basically creates a solid cube, a unit solid cube. Basically, I am taking it as 1.0, so it will create a unit solid cube, right? Now, remember, this is our z-axis, this is our x-axis, this is our y-axis, and we are looking at 2, 1, 2 position of camera, right? That is along x-axis 2, along y-axis 1, and along z-axis 2. That's exactly where we are positioned and looking at. Basically, the camera is positioned at that place and looking at the object, the origin, right? Now, my idea is I'm going to create a function for wall, and I'm going to create a function for table, basically table top and table leg together, and I am going to create place a teapot, right? So for teapot also we have a function called glut teapot. So that function we will use. The teapot is not modeled by us. We will be directly using the inbuilt model function which is present to get the teapot. Okay. So we need 3 walls. Our idea is to call this wall 3 times and perform translation, rotation, and scaling however we want. Now, this is the solid cube that I get. Now, I want this solid cube to become the floor, right? I want it to become the floor. How do I make this as floor? Any idea? I have a solid cube. I want to turn this solid cube and make it the floor of the room. How do I make it? What translation am I supposed to, transformation am I supposed to apply? Shear, no. I have a solid cube. I just want it to become the floor. So I just have to apply scaling, right? I have to scale it. Along what axis? Along y-axis. The z-axis, the x-axis remains same, and z-axis remains same. I am not changing this dimension, that is x-axis. I am not changing this dimension, that is my z-axis, but I have changed this dimension, that is y-axis. By how much? I am passing the parameter called 0.02. By that much, I am scaling this object, and that becomes my floor. Do you guys understand this? What am I doing here? No, not rotate. I scaled the object. I just compressed it along y-axis, and that actually gave my floor. Okay. So now I will start the demo, and we'll go on explaining you the code. Then and there, however it is required, I'm going to explain you that. Right. So if I call the wall, and in the wall, I have this solid cube, and that would give me this output, right? Now, all three walls I am supposed to scale it. So I am scaling it. If I scale it, I would get this, right? So the scaling I am applying directly when I create the solid cube, because all three walls are supposed to be scaled. They are the solid cubes which are scaled. Similarly, I will take a solid cube and I will scale it along z-axis, y-axis, and x-axis to get the tabletop. Similarly, I will scale it with different parameters along x-axis, y-axis, and z-axis to get my table leg. So that's the idea. We are going to use solid cube and scale it and translate it however we want, and then use it, right? Now I need three walls, so I will take three walls. So I have three walls right now, but I'm not seeing them. I have only one wall. Why is that? I called it thrice, right? But I'm seeing only one wall. Why is that? Yes, they are overlap. Basically, you place them all of them exactly. All of them are at the same place. Now, tell me, you want one to be the floor and the other two to be the this, right? And this. Now, I want to rotate one along some axis and I want to rotate this. Now, if I want to get this wall, how should I rotate it? By how much should I rotate it? And around which axis should I rotate it? Z by 90 degree. Correct. Now, how about this wall? This one. Around which axis and by how much? Correct. Yes. That's right. Great. So that's what we will do. We will rotate them. Around z-axis, I rotated by 90 degree. Around x-axis, I rotated by minus 90 degree. I will tell you why minus 90 degree. It is not supposed to be plus 90 degree. It should be minus 90 degree. I'll tell you that why. Okay. So just hold on. Now I have this. Now let's see. Let's run the program. But all objects are rotated. All walls got rotated. How is that possible? Or why did it happen? That is because see, this rotate is applied to all the objects below it. This rotate is applied to all the objects below it, right? So if you want to separate each object's coordinate system and perform translation, then what we should do is we should first store the current coordinate system and then create the wall and then rotate it and then pop the matrix, that is retain our coordinate system back. Okay, so when we do this, we would get this z-axis rotation. See, z-axis rotation we got. Now, similarly, I will do that for x-axis. I got my x-axis rotation. All of them are around the origin, right? We know about rotation around origin. That's why we rotated around the origin. Now, this is what we got. So, right now, what happens is, you guys have to understand one small concept here. Whenever I rotate, right, whenever I rotate an object, right, that object is not just rotated, even that object's coordinate system gets rotated. Okay. Now I had a wall like this. You rotated the x-axis of this was this, y, this was z, and this was y. You rotated around z-axis, right? By 90 degree. So that is anti-clockwise direction, in this direction. So what happened? This x-axis got also, this coordinate system of this wall also got rotated. So the x-axis went to y, the y became z. Sorry, z is still the same. I'm so sorry. You have this object. This was x, y, and z. Now you are rotating it, right? So if you rotate it like this, basically, x-axis would be this, y-axis would be this, and z-axis would be this. You just rotated it. So this went up and this went down. So y came over here and this became x-axis. Is that clear? Did you understand the rotation of the coordinate system as well? Can you visualize that, please? Did you understand that? Yeah, okay, cool. So now, similarly, we had an object, we rotated it around x-axis by, this is where y I was doing minus 90 degree comes into picture. Look at it. X-axis, z-axis, and y-axis, right? Now, I want to rotate it clockwise. The reason is, I want everything aligned with respect to y-axis. One translation I can apply to get all of them back at one position. Basically, I can make all these walls to sit at the origin. I'll tell you that anyway. Now, if I rotate it by minus degree, what happened? This y came over here and this z came over here. After rotation. This is after rotation. This is for x-axis rotation. For z-axis rotation, what happened? For z-axis rotation, this y-axis is this, and z-axis is, sorry, x-axis is this. This is z, and this is x. And then you have the floor. The floor is not at all rotated, so the floor has x, z, and y, right? Did you guys understand the rotation or what I was doing? Rotation coordinate systems, what I told you now? Now I want to move this object half above, right? This one, the x-axis rotated one, half above, and this one half front and half up. This one half towards x-axis and half towards above, right? So right now I have my x-axis rotated object is like this, right? I want to get this junction over here. What I should do, I should translate this wall by x-axis and then z-axis. X-axis, if I translate it, I would get my wall here like this, and then I have to move it up by z-axis, right? Similarly, I have this object. This object is rotated around y-axis, so basically it's like this now, right? Now I want to bring this wall over here. So again, translation I am supposed to do along x-axis and z-axis. Over here also, I want to bring this position, this corner, to the origin. So what should I do? I have to translate it by half of this wall. This wall, all these wall size is 1, right? Unity. So I have to translate by x-axis by 0.5 and z-axis by 0.5. That will bring my object like this at the origin. Did you guys understand this? So translation, all 3 walls are supposed to be translated by 0.5 along x-axis and 0.5 along z-axis. Is there any doubt with respect to that? For all 3 walls, this is common. That's the reason what I will do is, I will apply translation in the wall function for all 3 walls. I'm translating by x-axis 0.5, by z-axis 0.5, and y-axis I have to slightly overlap the thickness of the wall, right? So half of it into the thickness, that is 0.02 I have taken. So the result what I would get is this. If you see, we have positioned it. Now if I don't do this, I would get something like this, right? Only one wall is moved, the others are not. Only along one axis you have moved, but along z-axis translation you have not done. So all 3 walls you have placed. Any doubts on placing the walls? Shall we look at the table modeling? Can we rotate by plus along x and translate accordingly? Yes, Ashwin, what happens is, if you translate along plus 90 degree, at that time you will have to perform separate translation. Right now, because I rotated it by minus 90 degree, I had to translate it along x and y axis positively, right? So if I had rotated it by positive 90 degree, then what would have happened? I would have got my object like this, z-axis, x-axis, y-axis, positive, right? So if I rotate it by positive 90 degree, then this becomes y and z would come down, right? I'll have to perform a separate translation. So that would be along different axes, not just along x and z axis. Because I rotated with minus 90 degree, I was able to perform it using x and y axis. Let's see if that has an effect. I'll show you. Just check it out. Did you see? It went in negative z direction actually. Because the z axis, if I had rotated this object along x axis by positive 90 degree, this z would go down, right, in anti-clockwise direction. It would come here. So it went down. Because I rotated in clockwise direction, z went up actually. This became z, right? So that's why it will come up, not down. So in that case, what you should do is you should just translate just for this particular wall. You have to translate it above. You have to use apply translation again. So that's the only thing. We just avoided it to apply translation multiple times again and again for all 3 walls. By rotating it conveniently by 90 degree, negative for x-axis rotation and for y-axis rotation along positive 90 degree around z-axis, we were able to translate all 3 walls in just along x and z direction. So that's the advantage, nothing else. So you could always rotate it by plus 90 degree, no problem. Did you get it, Ashwin? Okay, cool. So now we will look at the wall, the table. The table, whatever you create, is actually created at the origin. If you see, you have moved this wall by 90 degree up and down, right? So you have created it actually at the origin. Now you wanted to bring it at the center. So what you will do is for all the objects, this table, that is table leg and the table top, you are moving along x-axis and z-axis again by some amount. You can change these values and model it accordingly if you want. You don't have to remember these parameters as far as pushing power. See, you got the table into the scene, right, by applying this translation. Now let's see how to model our objects. I'll just retain the floor. I'll translate. I'll comment this. Okay. We are passing 4 parameters here. What are these 4 parameters in the table function? We are actually having table width, table thickness, that is along y-axis. Table width is nothing but the length and breadth of it, and leg thickness, that is the length and breadth of the leg, and the leg length, that is along y-axis. So basically these are our scaling factors, right? So we are scaling the solid cube with respect to these things. Now let's look at the table legs. Modeling table legs. So you are creating the table leg by creating a solid cube again. You got a solid cube at the origin, right? And then you are scaling with respect to the thickness along x and z axis and length along y axis. So that would give you this. This is common for all 4 legs, right? So you want to bring that leg by half, above half of it is below, right? The origin. So you got the complete leg above. Now it's on the top of the floor, right? So this is how you actually model a leg. So by calling table leg, you are actually modeling a leg at the origin, right? Now what you will do, you will translate it by with respect to the table width and the dimension what you have, you are translating it along x and z axis, and you got it at a certain position. Now you see you translated it, right? You are not popping, you are not actually applying the pop matrix here. So the translation, once you apply this translation, the origin is this right now. Whatever translation you apply would be from this position, right? So what you are doing is you are actually modeling another leg now. See, you got this. And then you're translating by them like this. Okay. Now, once you apply this translation, you get them properly. Yeah, they are on the floor, right? And the tabletop, actually, you are to create tabletop, you are creating a solid cube, and then this is the solid cube. You're scaling with respect to the table width and the height of the tabletop. Yeah, you got it scaled. Now you have to lift it up, right? So you have to lift it up by table length. So that's why what you will do is you apply table length. This will model you the table. I'll remove the wall. So I got the table here. Now what I will do is to model the solid teapot, I would create a solid teapot of certain size 0.09. If I create the table pot with size 0.1, this is a unit teapot. This is a complete teapot. So I have to scale it down, or the dimension of the teapot should be less. That's why I am taking it at certain, size 0.09. This is, of course, the value of 0.09. How did we figure out? We would use it and try it and get the appropriate size. So if you don't get it, and you don't have to remember this size in the exam, you can try and plug and play. It's okay, right? Now let me comment table. So you would see the solid cube at the origin. See, this is the solid cube, right? Sorry, this is a teapot. Now you have to translate it by some amount to get it to the center of the scene along both x, y, and z axis. So you have translated it along y axis, and x axis and z axis. So you don't want the table to rise up. That's why you're not, translating by y axis. But you want this to sit on the top of the table. That's why you are translating the teapot by 0.4 along y axis as well. This will give you the complete scene with teapot sitting on a table, and the complete scene being illuminated by the light source in the scene. And what you are actually seeing is the effect of reflection based on the material properties that you have assigned to this scene. So that's about this program, guys. Any doubts so far? When do we know we need to push matrix? So actually, it's a good question. If you are, I'll show you, wait. You can, by pushing the matrix, you are separating the coordinate system of the object with the world origin what you have. Now you see, I have this at certain distance. So whatever translation you perform would be relative to the current position of the origin. If you want to separate it out, you would do that. See, this is the first leg that I have kept. Okay. The second leg, whatever I am keeping, see, this is the first leg. I have stored the current origin. Current origin for me is basically this, and then I have applied the translation, right, on this object. So my origin of this object is shifted. Now this is the current origin, right? This is no more the origin. This is the current origin for me. Now what I will do is, if I pop, right, I would get my origin back. That is, whatever object you model next should have to be translated from this position. But now I am not popping, so I'll have to translate my object from this position as the origin. So the next object what I get is basically this, right? If you see here, this is negative z-axis, right? You have placed it in the direction of negative z-axis. So you create this object, you actually would get it overlapped with this leg that you have already at this position. This is overlap. Now you are moving it in towards this direction. This is your origin for now because you have not yet popped, right? So negative z-axis you are translating. You got over here, right? Now this is your origin. Basically, right now your origin is at this place, the second leg what you have placed, because you are not popping it, right? Now the next leg what we have kept is the diagonal leg of it. This one. So from here, I have to move along z minus x-axis and plus z-axis, right? So minus x plus z is what the translation I would have done for this. If you see minus x of distance and minus z of distance is what I have taken. And now my origin is at this leg. I'll have to go here, right? So for this, what I will do is I would go by applying negative z translation. I got my table leg. So what we did here is, see, all these objects, for all modeling all these objects, we push the matrix and pop the matrix. Basically, every object we're creating at this as the origin. This is the sense, the intersection of all these three walls, that was treated as an origin. Because you are popping every time the matrix you have pushed, you place an object appropriately and then you pop off. So when you pop off, you go back to your original origin. But while you are placing this legs, right, you are not popping it. So because of that, you are not going back to your origin. Your origin would be the current translated position. So you are placing these legs relatively and then you are popping it. The moment you pop it, you will go back to your original origin. Since you went back to your original origin, you could place the teapot. Relative to the intersection of the wall origin. That's the wall coordinate system origin, whatever we have. So basically what we have to understand here is every object will have its own coordinate system. We can in fact separate it out from the world coordinate, reference coordinate system that we take. We can do that using pushing and popping. We store the coordinate system, play around with the current coordinate system. Once we want to get back to the coordinate system, we just pop it. I hope you understood, Ashwin. Is there any doubt? Did you understand? Okay, cool. Any doubts? If you guys have any? If not, thank you. Thank you, ma'am, for taking the attendance. You guys can leave. Understood? Shruti, no, which part you did not understand, Shruti? Inside the cubes to get the walls. Oh, no doubts. Okay. I didn't get your question. You can unmute and speak, Ashwin. Oh, you mean to say the surfaces of the cube itself is the wall, like that? Oh, I understood. In that case, what happens is, oh yeah, I got it. So if you keep that, you would still have the top also, right? You would still have the top. You can do that. That can be done, Ashwin. You can do that. That's no problem. You can position at the corner and place the camera and see the origin, you can still do that. Yes, it can be done. You guys can try that. So in that case, what happens is the light source you will have to keep it inside. I'm not sure in this case the inside cube will be illuminated or not, because light source, it depends on where we keep the light source. You will have to take care of that. Number one. Number two, the other objects, that is the other surfaces of the cube, that is the top and the left and the front, all these will be there. You will have to position such a way that you don't have to get that in the visualization. So camera position and lighting position, you will have to take care of that. Are we clear, Ashwin? Okay, fine. Thank you guys. Thank you, Ashwin.